Hello friends, my name is Derek Carter, and in this video we're going to start looking at a little bit more details of TensorFlow. So the TensorFlow API. So we were introduced to that previously in this course, and we're going to get into some of the more details of how the TensorFlow API works and what you can do with it. So So training neural networks revolves around the following concepts. So, you need to have low-level tensor manipulation, and that's basically what the TensorFlow API provides, all right? So the infrastructure for TensorFlow that underlies what you can do provides things like tensors, right? So these are representations of matrices and vectors, basically uh, abstractly, we call those tensors. So we saw an example of that. So in particular, you need kind of a special one, tensor variables that can that can hold the state of the network that you're working with. And then operations on those tensors. So we went into a little bit about tensors like matrix multiplication, the rectified linear unit, addition, those kinds of things. So it's good to have a feel for kind of geometrically what it means when you're doing those sorts of operations on data as it flows through the network. And then backpropagation. So a way to compute the gradients of these layers. So the layers of a neural network is a sequence of these kinds of tensor operations over your tensor variables. And you need to compute the gradient so that you can update the network state in order to improve the performance of the network. Right? So we did see a brief example of GradientTape. We'll go into a little bit more detail of that in this video. And then you have high-level concepts for deep learning. This is really kind of what the Keras API gives you. So the idea of layers and different types of layers that you might want to put together for a neural network architecture. Loss functions, so the different most popular ones are all provided so that you can use those in the Keras API. An optimizer and advanced optimizers, which which basically updates the weights and determine how learning proceeds. Metrics for performance evaluation, and a training loop. So this is basically what the fit function invokes in the Keras API to iterate over the stochastic gradient descent algorithm, updating the ways to improve performance. And so, for example, just real quickly, if you're like a researcher and you want to build like a new optimizer, that would be an example of something that might not be available. If you're researching how to improve on current advanced optimization techniques, you could implement that in TensorFlow, but then use everything else in the Keras API with your new optimizer and compare that to existing optimizers. So to do anything with TensorFlow, we're going to need some tensors. So tensors need to be created with some initial value. So basically, TensorFlow has immutable and mutable tensors. So tensors that can't be modified versus tensors that can. Okay, so the default ones that you get are the immutable kind, right? But a lot of this should look familiar if you have used NumPy before. So most of kind of the conventions are the same here as in NumPy array. So, but these are actually immutable. We can't change the tensors that we show for the first ones here, but we can create a tensor that has 2 rows and 1 column of all ones. So there's functions like ones and zeros, and functions for creating tensors with random values. So by default, these are drawn from a random normal distribution here, or a random uniform distribution here. So I already mentioned, the default ones we're using here so far are immutable, which is different from NumPy. So if you create a NumPy array, you can actually modify it. So here we created an array of all ones that had a 2 by 2 shape, and we modified one of the elements. But if you try to do the same thing, so notice, I mean, the syntax is mostly the same in TensorFlow. We create a NumPy tensor, but we index it in the same way. But if we try and modify that, it actually generates a type error. So, I mean, but it does beg the question. So, you use a lot of time, often you'll use a TensorFlow variable instead, which is going to be a mutable version of a tensor. And you normally initialize those, though, with an immutable tensor. So, we had a TensorFlow variable in our first example using TensorFlow. So these are just some more examples. If we create a variable where we initialize it to something that has this some random variables with 3 rows by 1 column. We can update an existing mutable variable by assigning it some new values. And we can assign specific things in the tensor. And there's assign add and assign subtract, kind of equivalent to plus equals and plus minuses that you can do. So, by the way, I mean, if you assume that the things in the textbook go in sequence, it's a little bit different from what they show in the textbook. So if you have v has these values and you do a plus equals of 1, it should become 422 here in this case. So TensorFlow offers the usual range of mathematical operations. So, anything you can do in NumPy, you should be able to do in TensorFlow, although sometimes you don't have the same kinds of things available. So, for example, I should check this out. I'm not 100% certain, but, in NumPy, we might have just done something like b equals 8 squared. So use the 2 stars to raise something to a power. So that's defined in NumPy to do a vectorized raising to a power. To do that, or like a square root if you raise it to half. But anyway, so there should always be an equivalent if you can't do it using kind of the built-in operators of the Python language. Squares and square roots, addition and multiplication, or even element-wise multiplication. There is a matrix multiply, of course, which does the same thing as the dot function to do the dot product or matrix multiplication from NumPy. So all these operations get computed on the fly. So this is why we call this eager execution, and this is why we're able to print out the results directly after that. So even if a computation graph is being built, still those computations are being done as you execute them in like a Python notebook. So you'll understand a little bit more about that later when we talk about eager execution here. So far, I mean, what we've shown here, TensorFlow looks like it's basically just NumPy, right? So, but the big difference then is that by defining computation graphs and then calculating gradients, that's built into TensorFlow. So these tensors and variables, it will automatically do that when you're performing calculations within the scope of what's known as a GradientTape here. So we can retrieve the gradients of any differentiable expression with respect to any of its inputs. We just have to open up one of those GradientTape scopes and then apply some computations within that scope. And then when we're out of the scope, we can then use the gradient function on the tape to automatically differentiate and retrieve the gradients for us. So a simple example, if we have a variable and we do square, basically we're doing the function y equals x squared. So from basic calculus, you should know that the derivative is going to be 2x. So at the point 3, if we calculate the gradient of the input variable 3 with respect to our result, the gradient should be 6 here, right? 2 times 3 is going to be 6. So so most commonly we use these to retrieve the gradients of the loss of the model with respect to the trainable weights, right? So these are going to be mutable parameters that represent the current transformations that happen in a layer. Okay, so this is basically what we normally want to compute, where we will have different sets of weights on different layers, but we will need to compute the gradient of for a set of weights somewhere with respect to the final loss that we had at the end of a calculation. So by default, only trainable variables are tracked. So only the mutable kinds of things are going to be tracked in a gradient tape. So if you wanted to track the gradients of a constant tensor, you have to manually mark it to watch it. So I don't know. So we might run into something in this course where we need to do something like this. Okay? So here, if we have the input, as we're inputting as a constant tensor, we have to actually watch it in order to be able to compute the gradient of the input with respect to the final result here, the same function that we were doing before. So notice you get maybe an unexpected result if you don't know that. So it's not tracked by default. So even though gradient doesn't complain, you just get no result if you do that. So yeah, why is that necessary? It's basically this stuff is kind of expensive to do computationally. So the default is that TensorFlow and the GradientTape is trying to only keep track of the computation graph of the things that are absolutely going to be required to be needed. So that's usually going to be the mutable variable tensors is the only thing that represents weights or the trainable parameters of the network, and anything else shouldn't be kept track of by default, but you can if you need to. So yeah, the gradient tape can compute second order gradients. So the first order object, first order of an object is position over time is its speed, and then the second order is the gradient. So it's like the first and second derivative. So you have to recall a little bit of physics if you ever took a physics course to kind of get the basics of what's happening here. But yeah, I mean, basically this gives the computation to be able to figure out the position given the time of something falling on vertical axis where it's falling in Earth's gravity. So it's actually, this ends up being because we're using the Earth's gravity constant of 9.8 meters per second, right? If I remember right. So here, yeah, if we have a gradient tape, inside of a gradient tape, we're actually computing the first and second order gradients of our calculation here. So this is basically saying that the acceleration is going to be constant. So that's our first order effect here. But the speed is going to be increasing, and in this case, we're ignoring air resistance, so we don't have a terminal velocity. So presumably, this would keep just increasing in its speed, getting faster and faster. It's second order property here. Yeah, so we have a big one. So anyway, but yeah, so you can actually get first, second, third order effects if you need to, gradients. So you might need that, for example, if you need to build your own optimizer and want to do something with momentum. That's a second order effect. So you might have to do things like this. So for the rest of this video, we're going to be looking at this example of building a linear classifier from scratch using TensorFlow and some of the concepts that we've been talking about so far. This is a really good example. I encourage you to spend a little bit of time with this, make sure you kind of understand it. This is also kind of similar to one of the assignments I'm planning on having us do for our class here. So, like it mentions, I mean, if you were applying for a job where they expected you to have a good number of years of experience with TensorFlow and Keras, I mean, this could be conceivably something like a job interview, kind of a question you might get. So basically in this example, we're going to build a linear classifier. That's basically logistic regression. So we're only going to have a matrix multiplication by a set of weights and adding in a set of bias terms. That's basically what happens in a single single logistic regression, just using plain TensorFlow. Okay. So I won't discuss too much how the example is created. So, you know, it helps again to know a little bit about some statistics, but this is basically creating two samples of 1,000 points, one with a mean at 0.3 and the other with a mean at 3.0. And we put these set of points together and create our training label. So we'll have one of them with a training label of 0 and one with a training label of 1 for the setup for our learning here. Yeah, so this is our targets that's doing that. So anyway, this is the data. So a classifier, if you've taken a machine learning course, is basically, if we're doing a linear classifier using like logistic regression, the result of that is going to be a line. So we have two features. You can think of this as feature 1 and feature 2 of the data set. And so the best fit line is going to be something like around here that will maximize the most number of correct classifications. I'll just call this class 0 and class 1. So let me see if I can remember for the color here. I just had to double check that real quickly. So, right, we have negative samples and positive samples. We're going to use 0 as the label for the negative samples and 1 for the label for the positive samples, which is usual for this type of a binary classification task. So, for example, the first sampled item from the negative samples is at 0.85, 0.36. So somewhere up here, right? So I probably should have go ahead and add like a legend here on this, so I wouldn't have to go and look this up. But the dark ones are going to be our negative samples, and the yellow ones will be the positive samples in our example. So here we're going to create a linear classifier using TensorFlow variables. So basically, you know, what happens in linear regression or logistic regression is you have a set of weights and a set of biases, and you're just performing the matrix multiplication and of the weights times the inputs, and then adding in the biases to get your prediction of what your output should be here. So so in TensorFlow, we can create two variables, W and B, we'll call those, where we've got two inputs. So we have to have a particular shape for the weights, two inputs and one output. And the bias is just a single value that's added on there. Let me take a look at what we get here. So we start off with just initial random values. So this is typical for when you have like weights and biases in a layer. The weights are going to be some small random value, although just in this example, we just set them to some random value between 0 and 1. And we set the biases to 0. So that's often the case. So the forward pass for a layer like this for logistic regression, you know, so we're doing an affine transformation here. So we're doing these just two tensor operations, multiplying inputs times W and adding B to get the output. Okay. So so you can think of that as performing the weighted sum and adding in the biases. Right? So yeah, if you kind of expand it out, what's happening there, the one weight gets multiplied by the first dimension, so we can call that the x-axis, and the other weight by the y dimension, and then B gets added into those with the prediction. So these represent what we'd think of as the theta 1 and theta 2 parameters for our network here. So next, we need a loss function. So in this example, we'll just use the simple mean squared error. So notice this is taking the error is going to be the difference between the targets and the predictions, squaring that, and it's actually returning averaging that, right? So this is the mean squared error. So for categorical, so for a classification task, we might normally use something a little bit more complicated, like the categorical cross entropy, but this should suffice, especially since this data isn't too tough to separate here. So, oh, and notice, I mean, these are all vectorized, so what's going to be coming in these are TensorFlow tensors as inputs and outputs. So, if the inputs have 2,000 items like they do, the result of the affine transformation here will be 2,000 predictions. So both of these will have 2,000 predictions and 2,000 targets here. But this will get reduced to a single value representing the loss here, the mean squared error loss, when we use this function. So next is a function that's going to take care of performing the basic training stack. So this is really the implementation of gradient descent here. So this takes the training data and it's going to update our weights and our bias terms so that for each step it reduces the loss by a little bit. So yeah, I mean, I really agree with this comment from the tech boy. This is a neat kind of basic example of the power of using TensorFlow. So again, it's going to create a computation graph for us while we're doing the forward pass. We can use that to ask it to give us the gradients, and then we can use those just directly to update the weight. So here, if we look at it, the updates of the weight is done by, we do this assign sub. So this is doing a minus equals. So basically, whatever the current values of the weights are, we subtract the gradient with respect to W times a learning rate. So just using 0.1 works good in this example. Same for bias here. So, if we know the gradients, we want to go in the opposite direction, which is why we're doing the minus equals subtracting. That will end up with a new set of weights and biases for each one of the training steps here. So this is really full batch training. So this isn't mini batch or stochastic gradient descent. So for every training step, we feed it the full inputs and the full targets in this example. We could easily turn this into a mini batch by still with the same function, but by sampling batches of inputs, and there are targets to do that. So yeah, full batch training, like we're going to do here in the cell. I didn't mention this before, is going to be. It's going to give you steps on the gradient that are much more likely to be kind of in the right direction, right? So as opposed to like a smaller batch or just training with a single input, a single sample. So when you have smaller samples or down to one sample, that sample, the direction you go that reduces the loss would be, of course, great for that one sample, but it might not be really great for many of the other ones. So you get a lot of noise the smaller your samples are. So anyway, the larger your samples are, if you're using full batch training, you don't need as many training steps, although it's much more costly to do each epoch. So a training step is usually referred to as an epoch in deep learning and neural networks. And typically you can use larger learning. So in this case, this loop is really actually implementing gradient descent. Right, so we're showing what the loss is. So initially, the loss that was calculated was this. You notice that for each step, we just hard code it to go 40 steps. It should get smaller and smaller, right? Because we're always going to be choosing. I mean, it might get to a point where it's not changing or not changing much, but it should never go up when we're doing like a full batch. When we're computing the gradients for the full batch. So you'd see more randomness if you're doing updates on mini batches or on single samples. But yeah, when you do full batch, it would be a lot less randomness. So here again, we're skipping over a few details. We're just using a basic activation function, but still, just using a threshold of 0.5. Will allow us to define a line here. So basically the line that's being defined is whatever the final values of the weights and the bias ended up being. If we set that equal to 5, there's going to be defined a line in our two-dimensional space. Anything below that line, so below 0.5 will get predicted as a 0. Anything above that line will get predicted as a 1 for data retrieval. And as you'll see that, the data, they're not completely separable, but it's not too tough of a task. And this is good enough using the mean squared error loss function with no too much of activation. So in some sense, for the loss function that we use, that should be the line that gives the best results for the data that we fit it with. A few of the points ended up a little bit above here for the yellow, but not too much. So this is really what a linear classifier is all about. So we're basically finding the parameters of a line if it's a linear classifier, or if it was higher dimensions than 2 dimensions, it would be a hyperplane that separates the classes as best as possible. Okay, so that's it for this video. In this video, just to summarize what we did, we dove a little bit more into the details of the TensorFlow API. Gave you a little bit more of an idea of what's happening there, how the gradient tapes work and things like that. But in particular, most of the last half of this video, we looked at an end-to-end example of implementing gradient descent using the basic TensorFlow API and the gradient tape. Okay, so I do encourage you. That's a very good example. Spend a little bit of time on that. That's one of kind of the fundamental sort of concepts. There's a lot of fundamental concepts in that small example that will kind of help you understand how deep. That's it for this video. I hope you found it interesting, and stay tuned for our next one where we'll go look into some of the details of the character.